In this video, we want to take an equation system and solve it using the matrix inversion technique. So let's take our first equation in our equation system, which is 3y minus 4x equals 4. And the second equation in our equation system is 2y minus 2x equals 3. And whenever you write down these equation systems and you want to solve them using matrix algebra, make sure that the first variable in each equation is the same, in our case y, and the second variable in each equation is the same, in our case that would be the variable x. If you wanted to, you could reverse the order. You could rewrite the first equation as minus 4x plus 3y equal 4. But if you do that, be consistent and write the second equation down as minus 2x plus 2y equal 3. Okay, now the first step in solving this equation system using the matrix inversion technique is to write down your A coefficient matrix, your X variable matrix, and your D matrix of constant terms. So let's form our A coefficient matrix, which is going to be 2 by 2, since we have two equations and two unknowns, y and x. The way we form the A coefficient matrix is we simply take the coefficients of each of our variables in order. So for the first row of the A matrix, we take the coefficient of the first variable y, which is 3, and then we take the coefficient of the second variable x, which is minus 4. For the second row in our A matrix, we take the coefficient of the first variable y, which is 2, and then the coefficient of the second variable x, which is minus 2. To form our X variable matrix, we take all of our variables in order, y first and x second, which is the case for both equations, and put them into a column vector, which in our case is a 2 by 1 matrix, and that represents our X variable matrix. And then we need to form the D matrix of constant terms. And we simply take the constants in each equation in order and put them into a column vector, 4 and 3. So D is a 2 by 1 matrix or a column vector, 2 rows, 1 column. Now, the next question we want to ask ourselves is, does this equation system possess a unique solution? Well, it will possess a unique solution if the rows are linearly independent and the matrix A is non-singular. And of course, if that all occurs, the determinant of A will be non-zero, and the inverse of A will also exist. So to see if we have a unique solution to this equation system, all we need to do is start by looking at the determinant of the matrix A, which in our case is minus 6 plus 8, which comes out to be plus 2, which is not equal to 0. So we know a unique solution to this equation system exists. A is non-singular, and we also know that the inverse of A will exist. The next step in the matrix inversion technique to solve this equation system is to find the inverse of A. But to do that, we need to start out by finding the cofactor matrix of our A matrix. So recall how we do that. We have to replace every element in the A matrix with its cofactor. And so our cofactor of element A11 in the A matrix is going to be minus 2. The cofactor of element A12 in the A matrix is going to be minus 2. The cofactor of element A21 is going to be plus 4. And the cofactor of element A22 is going to be plus 3. From there, we can find C transpose, which is the adjoint of our A matrix. And it is simply minus 2, 4, and 3. Now we can go directly to the inverse of A, which is 1 over the determinant of A, times the adjoint of A, which is the transpose of the cofactor matrix, or C transpose, minus 2, 4, minus 2, 3, which comes out to be minus 1, 2, minus 1, and 3 halves. From there, recall that the original equation system could be represented using matrices as AX equals D. And from there, we showed that the solution to this equation system in matrix form can be expressed as X is equal to A inverse D. Well, let's just see if we can fill in all of these matrices in that last matrix equation. The X variable matrix was YX, it's a 2 by 1 X variable matrix. The inverse of A we just solved for, which contained the elements minus 1, 2, minus 1, and 3 halves. And the D matrix of constant terms was 4 and 3, a 2 by 1 column vector. Okay, so let's perform these matrix operations. This implies that YX, the X variable matrix, is equal to, we have a 2 by 2 times a 2 by 1. So those matrices are conformable for matrix multiplication. It will result in a new matrix, which is of dimension 2 by 1, 2 rows, 1 column. So how do we find this first element? This is our product matrix of these two matrices multiplied together. So this is the element in the first row, first column. So we take the first row lead matrix times the first column lag matrix. Minus 1 times 4 is a minus 4, plus 2 times 3 is 6. This element, second row, first column, second row lead matrix, first column lag matrix. Minus 1 times 4 is minus 4, plus 3 halves times 3, which is 9 halves. And let's rewrite this as, again, YX. Here's our X variable matrix. I'm going to write this as 6 minus 4 is 2. And the minus 4, I'm going to rewrite that because I want to put it over the same denominator as this second term here, which is over 2. So I want to multiply the numerator and the denominator 1 by 2, and I convert that to what? Minus 8 halves, same as minus 4, plus 9 halves. And if we simplify this, our X variable matrix is equal to a 2 by 1 matrix containing the elements 2. 9 halves minus 8 halves is 1 half. And what does this expression mean? When we say two matrices are equal, they have to be of the same dimension. And it also means that these two matrices have identical corresponding elements. So this implies that Y is equal to 2 and X is equal to 1 half. And that is the solution to our original equation system. How can you check to see if that is the solution to the original equation system? Go back to the original equation system right here. Put in that value of Y and that value of X into each of these equations and make sure each equation is satisfied.